Hi everyone, I'm Tong, postdoc at the University of Cambridge. It's my great pleasure to speak about my work on the parity violation from home workshop. So, as a topic we all know and love, parity violation was famously discovered in electroweak physics almost 80 years ago. In the recent years, however, there is a renewed interest for parity violation in a different context, namely cosmology. Hence these nice parity violation from home workshops. There are plenty of talks at this workshop that explore various observational signatures of parity violation in real cosmological data. In this talk, however, I will give a theorist's perspective on why parity violation is interesting and how it can be wielded as a test of fundamental principles and a smoking gun of new physics. This talk is based on our recent work this May and two earlier works in collaboration with David Stefanisson in the University of Nottingham and Yuhan Zhu from IBS in Korea. So let's begin. It's widely believed that our universe starts with a Big Bang, which is followed by an inflationary period. The exponential expansion of the universe stretches quantum fluctuations outside the horizon and prepares the initial conditions for the late-time cosmological evolutions, such as the cosmic microwave background and the formation of large-scale structures. By looking backwards in time and measuring correlation functions of, for instance, the CMB temperature anisotropies, we can trace this primordial correlators and the origin of the underlying model Lagrangian of inflation. And this pipeline constitutes as some sort of a central dogma of primordial cosmology, in my personal opinion. For example, in the vanilla single field inflation scenario, the inflaton couples minimally to gravity, and the two-point function of curvature perturbations tells us the inflation rolling speed in Hubble units. And the two-point function of the tensor perturbations, namely gravitons, tells us the Hubble scale in Planck units. And the three-point function gives us consistency checks in the squeeze limit. Going beyond the minimal case, one can introduce the so-called EFD of inflation, in which the three-point correlator of curvature fluctuations informs us the sun speed and the UV cutoff information of the effective field theory. And one can then go further by introducing massive fields and couple them to the visible sector, such as the inflaton. And then the squeeze limit of these three-point functions of curvature fluctuations exhibits a characteristic oscillation known as the cosmological collider signals. These cosmological collider signals probe directly the particle spectrum during inflation. So in summary, cosmological correlators are powerful probes of the primordial universe. But the big question is, of course, can we detect them? So what we do know now is the curvature power spectrum at 2 × 10⁻⁹ with a slight red tilt. However, we do not know the two-point tensor correlator, namely the tensor power spectrum, nor the 3 and 4-point functions, which are non-Gaussianities. However, future observations are expected to improve both the tensor power spectrum and primordial non-Gaussianity detection by roughly 1 to 2 orders of magnitude. So cosmological correlators remain a promising smoking gun towards new physics. On the theory side, however, we also face the challenge of computing and understanding the structure of correlators in inflation or de Sitter space. The loss of time translational symmetry in de Sitter and inflation implies the non-uniqueness of vacuum and particle production, while interaction vertices no longer conserve energy. So the exact solution of a general cosmological correlator is necessarily complicated. They're often functions of kinematics that involve infinite series, hypergeometry functions, Appel functions, Mayer G functions, Cambet-Fourier functions, and even an infinite sum of all these complicated mathematical functions, special functions. Henceforth, trying to find exact solutions may not be the most efficient approach to understand the correlators, especially given these immense mathematical complexity. Therefore, in this talk, I'm going to ask another question, namely, can there be simple and testable relations among complicated correlators? If we can find a relation that expresses a complicated quantity in terms of other complicated quantities, but each of which are as simple and algebraic, and with a simple relation f, the observation of these relation among different complicated observables might give us a cleaner information about the underlying physics. In search of clues to address this question, let us shift to the so-called wave function approach for primordial fluctuations. So in this wave function approach, the evolution of the quantum fields in inflation is symbolized by some perturbative Feynman diagrams that computes the transition amplitude from the Barnes-Davis vacuum in the far past to some kind of field eigenstate at eta naught, which is basically the end of inflation or the reheating surface. Then after you obtain the wave function of the universe via a path integral over all histories of the evolution, you can obtain correlators by doing a simple Born rule, as in quantum mechanics. The wave function is then conventionally parameterized as an exponential of a sum of nth order wave function coefficients multiplying n factors of boundary fields and the momentum conserving delta functions. In the Born rule, one must take the modular square of this cosmological wave functional, which means that only the combination of psi nk and psi n minus k can enter into the correlators. And for convenience reasons, we shall call this combination rho as wave function coefficients, just for convenience. But one should really realize that this is a combination of the two. So for example, at tree level for less than 4 points, the dictionary reads as follows: B2, which is the power spectrum, is simply 1 over rho 2 minus 1 over rho 2, where rho 2 is the 2-point wave function coefficient. B3 is proportional to rho 3 with some factors of 1 over rho 2, that means the power spectrum. And then B4 is given as a connected piece plus a single cut piece of rho 3 times rho 3 plus 2 permutations from other channels. And this pattern just goes on to higher points. And on the right is a diagrammatic representation of these dictionaries. Interestingly, in the work last year, we found that this infinite dimensional dictionary can be nicely packed into a functional form that states an exponential of correlators is given as a functional Fourier transform of another exponential of wave function coefficients. And the nice thing about Fourier transform is that its inversion takes exactly the same form as itself up to factors of I. Therefore, the function of Fourier duality implies the existence of a hidden Z4 symmetry in the dictionary that interpolates between correlators and wave function coefficients. Which means if I swap the rho of rho and B, this dictionary will look exactly identical up to I factors. And we check that we've been able to prove that this duality is valid to all orders in perturbation theory. For instance, let's look at our dictionary up to 4 points again. Suppose we would like to solve rho in terms of B. One can of course spend the effort to solve recursively order by order these algebraic equations. Or with the Z4 duality, one can directly map rho and B onto each other, landing exactly at the correct result. And this duality therefore simplifies this calculation greatly. So far, everything seems just mathematics. So where is the physics? Well, physics kicks in by imposing constraints on the wave function coefficients. For instance, one can imagine that there are some fundamental principles on such as unitarity, locality, analyticity, etc. And these fundamental principles pose certain functional constraints on the wave function coefficient rho. Now we can use our duality to invert the dictionary and immediately translate any of these constraints for rho to a constraint that is directly in terms of the correlators B. And hopefully these relations are simple, and it directly tells you that there's a hidden connection between different cosmological observables. By testing these formulas, one can perform a direct test of fundamental principles without the need of actually solving the wave function coefficients nor the correlators. As a concrete application, we consider the cosmological reality theorem, which is something we proved back in 2023. Namely, if one assumes a bunch of fundamental principles and some mild assumptions on the field contents, the tree level wave function coefficients of massless fields must be purely real. And we know that for Hermitian operators, taking a complex conjugation in momentum space is equivalent to taking a parity reversal. Therefore, these Rhoans, which are a special combination of these science, must actually be parity even. Now, this is a direct constraint on the wave function coefficient rho. If we use the duality, the Z4 inverted dictionary, to translate this constraint to a constraint on the correlation functions, we immediately arrive at a correlator to correlator factorization formula, which states that the parity-odd correlator of massless fields must consistently factorize into a structured sum of lower order correlators. And this is valid for any kinematics at any endpoints. There's really an infinite tower of such factorization formulas, these CCF formulas. And these CCF formulas are a manifestation of these fundamental principles and assumptions. Diagrammatically, one can represent these CCF relations by these equations. At 4-point level, the parity-odd B4 must factorize into a B3 times B3 with a light state in the middle. At 5-point level, the parity-odd B5 factorize into a B3 times B3, B4 times B3 bit, and a B3 times B3 times B3 bit. And there's an infinite family of such relations. And we stress that all these daughter correlators are correlators and thereby are in principle observables. And this is to we do not require any analytic continuation, and these equations are valid for any physical kinematics. This is to be contrasted with the cosmological optical theorem, which requires flipping some positive energies to negative values. This factorization also occurs for any kinematics, even away from the so-called soft limits and the OPE factorization. So at this stage, we have successfully uncovered simple hidden relations among observables. And most surprisingly, such hidden simplicity is a unique privilege of the parity-odd sector. And so far, no such simple structures have been found for parity-even sector. They are just still complicated. And this is why I think cosmological parity violation is interesting and inspiring, even from a pure theoretical perspective. And of course, in eventuality, every theory always needs to confront with experiments or observation. Therefore, in the work earlier this year, we set out to look for concrete realizations of these CCF relations. Essentially, we are looking for hidden CCF correlations, relations among different observables that could exist in the actual cosmological data. And interestingly, we did find an example in gravity. It turns out that in cases where the inflaton non-minimally couples to gravity via a Trans-Simons term, parity can be violated in the scalar 4-point function via the exchange of these parity-violating gravitons. And suppose one were to compute it via the conventional in-informalism, the calculation turns out to be very complicated and subtle due to the spurious IR divergences, which eventually cancel if you treat the mathematics carefully. However, if you just directly apply our CCF formula, which then directly predicts that the parity-odd curvature trispectrum will neatly factorize into a double copy of Maldaceno's curvature graviton mixed bispectrum, and this weighed by a parity violating graviton power spectrum. And this double copy relation is a direct consequence of the fundamental principles and is ready to be tested in actual observational data. To summarize, in this talk, we argued that parity violation is interesting even from a pure theoretical point of view. And by uncovering a Z4 duality in the dictionary of wave function coefficients and correlators, we proved an infinitude of CCF relations that link cosmological observables to each other via parity violation. In particular, the application to gravity shows a concrete double copy formula that can be potentially tested with observational data. Thank you for your attention.